Alright, Coach Hewitt here. I'm in the literal Hewitt House of Learning. Got my whiteboard, so my new classroom. We're going to talk about U-Substitution. So first off, so this is 10.2 if you're looking at your stuff. So first thing that we're going to look at is getting a new marker, because apparently that one is toast. Okay, so I have an integral. I have 3x minus 4 raised to the 5th power. Now the purpose of U-substitution is so we have these integrals that we're trying to take, but we're integrating things that had been, like if I derived it, there would be chain rule that was involved, so some more complicated integrals. So what we're going to do is we're going to use the letter U, and it doesn't have to be U, we just call it U-substitution, we use the U. And we're going to use that U, and we're going to let it stand for something in our problem so that we can make it a little easier to look at when we actually integrate it. So for this particular problem, usually the U is going to be whatever is raised to a power. If there is no power, kind of whatever is the messiest part of the problem a lot of the time. So for this one particularly, you know, if something had been derived here, this inside part, this 3x minus 4, that's what would be chain ruled. So we're going to let U be 3x minus 4. Okay? And what we want to do is we want to change everything in the problem from x's to u's. So what we're going to do here is I have this dx. The only way that I can get a dx to plug into is to take the derivative of this part here. So if I take the derivative of u with respect to x, I'm going to get 3. I want to just plug in for dx over here. So what I want to do is separate the du and the dx. So if I multiply both sides by dx here, those dx's are going to cancel. And so for like after this problem, what I'll do normally is I'll say du equals, and then I'll integrate that thing and then just write dx, because you're always going to end up moving the dx over. So once I do that, I have now du equals 3 dx. Now if I look at my problem here, what I'm going to end up doing, and we'll use some different colors, is this 3x minus 4 right here is this piece inside of here. So this whole piece here is going to become u. Then we have dx. So I want to see whatever dx is going to equal. So if I want to get dx by itself, I can divide both sides by 3. So I have du over 3, so I'm going to do 1/3 du equals dx. Now I can see that dx is this portion right here, so I'm going to replace dx with this 1/3 du, and I'm going to have everything in terms of u. So when we do that, the integral is going to become u to the 5th 1 times 1/3 du. Wouldn't it be really embarrassing if I was teaching this to nobody and I didn't push record? I did, no worries. Okay, so u to the 5th times 1/3 du. So pull out our 1/3. And we have u to the 5th du. So then what I'm going to do is I'm going to integrate it, because this is something that's easy for me to integrate. I know that if I have u to the 5th, I'm going to raise it a power. Whatever I raise to, whatever power I raise to, I'm also dividing by that. So we have 1/3, and then we're going to have u to the 6th over 6 which is the same thing as 1/6 u to the 6. And then we always have to put plus c, so plus our constant. Then we're going to multiply. 1 times 1 is 1. 6 times 3 is 18. And then we have u to the 6th plus c. So here we've integrated it. Now to get my actual answer, I still need to have it in terms of x. So what I'm going to do is u is 3x minus 4. So I'm going to take 3x minus 4 and I'm going to plug it in where u is right there. So I get 1/18 3x minus 4 to the 6th plus c. And that's our first problem. All right, next one, 3x squared times x cubed plus 4 to the 5th dx. So here, what we can look at is, first of all, we need to figure out what our u is going to be. And so in this case, if I were to think about this, if this was derived, this x cubed plus 4, I would get 3x squared. Okay, and so what I'm looking for is when I take the derivative of whatever I'm making u, you know, if there's other pieces here, a lot of the times I would like it to be that other piece. So let's let x cubed plus 4 be our u. Now, like a lot of things in calculus, you may have to go down a rabbit hole. So I may have to say, okay, I think u should be this one thing. And if it ends up taking you in a weird place, you might have to go back and set a different u. The more you practice it, the better you'll get at figuring out what u should be. So then I'm going to derive. And this is where I'm going to stop writing du dx and then moving dx over because that's obnoxious, right? So I'm going to do 3x squared dx. And if I look at this, like if this was rewritten, x squared dx right here is the same thing that's on this end part right here. So if I really look at this, I have everything I would need to just plug straight in, okay? So I can change this into terms of u. So x cubed plus 4. So we're going to say the integral of u to the 5th. And then 3x squared dx is du. So I'm just going to plug in du right there. Now, if that's confusing, if you have a hard time visualizing plugging that whole thing in, what you can also do instead is I could have divided both sides by 3x squared right here. And then when I plugged in, I could have got 3x squared u to the 5th. And then for dx, I could plug in this du over 3x squared. And then what would happen is these parts would cancel and you would still get u to the 5th du. Either way works. It doesn't matter. I just like to write as little as possible. Okay, so then we're going to integrate. So this is u to the 6th over 6, or 1/6 u to the 6th plus c. I'm going to plug in u, so I have 1/6 x cubed plus 4 raised to the 6th power plus c. And that's my answer. so then we have the square root of 4x minus 5 dx. Okay? Y'all can laugh at the fact that I just stripped, it's fine. So this is going to be the integral of 4x minus 5 to the 1/2 dx. And I'm going to integrate that. So I'm going to let my u be 4x minus 5, which would make du be 4 dx. Now there is no 4 up there, so I'm going to move 4 over. And I'm going to get 1/4 du equals dx. Then we're going to plug in. So u to the 1/2 times 1/4 du. Pull out our 1/4. And then we'll integrate. Now this one we're having a little bit of trouble with at times, just with fractions. Make sure that you're doing good with fractions. So when I add 1 to 1/2, that's going to give me 3/2. And then dividing by 3/2 is the same thing as multiplying by 2/3. So I'm going to multiply by 2/3 there. And then always plus c. So then we have this situation where now I have 1/6 u to the 3/2 plus c, which is 1/6. And then u to the 3/2 is the same thing as the square root of u cubed. So if we change that over into a radical and we plug in our 4x minus 5, that's what we should get. Okay, next one. So for this one, when I'm looking at what I should plug in for u, like I said, generally whatever's raised to the power, that's what I use for u. At least that's where I start. So I'm going to start there, and we'll see if that works out. Okay. So we have du. Now, if I want to derive this, that's x to the 1/2. So I'm going to get 1/2 x to the negative 1/2 dx. Now, what's nice here is if we rewrite this, x to the negative 1/2 is 1 over the square root of x. Now, what I notice in my problem is that I have a square root of x on the bottom of a fraction. So if I rewrite this kind of where you guys can visually see this. Purple. Then this 1 over the square root of x and this 1 over the square root of x are going to end up being the same thing. So I can plug straight in for that. Okay. So what we can do here is move this 1/2 over. And so I could multiply both sides by 2. And I'll get 1 over the square root of x dx. So 2 du is going to get plugged in for that blue circle. And then this part here is just our u. So u squared, 2 du move our 2 out, and then we're going to integrate. So we're going to end up with 1/3 u cubed plus c. 2 times 1/3 is 2/3. And then our u is actually the square root of x minus 1. Cubed plus c. And there's our answer. So that's U-substitution for those types of problems. We need to talk about trig. Keep getting paranoid that we're not recording, but we are recording. Full disclosure, I already did this once. Not on the whiteboard, but on a piece of paper. Let's just say it didn't go well. All right, so trig. Okay, so this is really the part where we're gonna have to know our trig derivatives pretty well, because to recognize these different things, you need to be able to visually look and say, oh, that's a derivative of the other part. So here, if we're looking at this, we're trying to decide what u should be. And here, if I think about e to the cosine x, if I took the derivative of e to the cosine, I would end up getting e to the cosine, and then I'd have to chain rule cosine. So the derivative of cosine is sine. So kind of looking at when I take the derivative of something, where am I getting this other thing? So we're going to let u be cosine x in this case. So that is going to make du be negative sine x dx. And if we're looking here, we have sine x dx. And I know for some of us it's hard to visualize if it's not together. Okay, so what we can do is let's move this negative over here. So negative du equals sine x dx. So then I can say this sine x dx is negative du. So I'm replacing that with negative du because they're equal to each other. So I'm going to get e to the u times negative du. So pull out my negative, and I have e to the u du. Now the integral of e to the u is just going to be e to the u plus c. And so u is cosine, so we're going to get negative e to the cosine plus c as our answer. And you can double check yourself. I would always double check myself, thinking once I derive this, am I going to get what I started with? So the derivative of e to the cosine x is e to the cosine x. Chain rule the cosine x and you get negative sine. So once those negatives cancel, I would get sine x e to the cosine x. Okay, so let's skip to this one. So we have cotangent 3x dx. Now, your first thought might be to let u be 3x in this case. But then when you take the integral, you're still going to be kind of in the same place. So what we can do is we know that cotangent is the same thing as sine over cosine. And so if we pick, we know that the derivative of sine is cosine. So let's let u be sine 3x. So if we do our du here, we're going to get cosine 3x times 3. So let's move, oh, and then dx. So let's move this over to the other side. And we're going to plug that in where dx is. So we're going to end up with the integral of u over cosine 3x times du over 3 There's no one here to stop me because I did this completely upside down. It's cotangent, so it should be cosine over sine. That part stays the same though. So when we come over here, it should be cosine. Some of y'all were probably screaming at your computer the whole time I was doing that. Sorry, can't hear you. Okay, so 3 cosine 3x. And those will cancel. And then I can also move my 3 out here. It's the 3 on the bottom of a fraction, so it's actually 1/3. So we have 1 over u du in this case. So 1 over u, when we integrate that, I didn't finish it on my paper, but it should be 1 over u is natural log. I'm pretty sure it's natural log. So 1/3 natural log of u plus c and then we'll have, when we plug everything in, the natural log of sine 3x plus c. Alright, so there's that. So trig Okay, so we're doing some others here. So on the back side, so I'll tell y'all, we have this, I'm not going to do this whole problem, but we have e to the x over 3 plus e to the x dx. Now, one thing that you want to make sure that you recognize is the difference between needing to use U-substitution and being able to just simplify things. Okay, for this particular one, let's use U-substitution. So we can see that if I took this piece of it and I took the derivative of that, I would get that top part. Okay, so in this case, U is going to be 3 plus e to the x. So du is going to be e to the x dx. And we can see that in the top portion of this. So this piece right here is going to turn into du. So this is going to be 1 over u du. And like we just said, 1 over u is natural log. So we'll have the natural log of u plus c. And we'll just take our u part and we'll plug it in where u is right there. So natural log of 3 plus e to the x plus c. The second problem is pretty straightforward. You don't have to use U-substitution, so make sure you're not just blindly using it on everything, because there's things that it's not necessary to use on, right? Okay, so then we have this one. Now, one thing that you always want to keep in mind is if I take the natural log of e to something, the natural log and e are kind of canceling each other. So this is going to end up just being 2x. So there's no U-substitution needed here. I can cancel that, and then I can cancel x's here, and then I can just integrate normally. Okay, and then I want to do this last one. So cosine cubed x dx. Now, there's some lists of some trig identities there, and sometimes it may be kind of a puzzle where you need to use a trig identity. For this particular one, we have cosine cubed x, and if I let just cosine be my problem, like my u, when I take the derivative of that, I'm going to end up with a sine. There's no signs to cancel here, so it gets messier actually doing it that way. So I need some signs here. So what I know is that cosine squared is the same thing. So let's write that over here. Cosine squared is 1 minus sine squared x. So that's a way that I can get a sign in my problem. So what I can do is I can change this into cosine, not CO2, cosine squared times cosine. Then we can change that into 1 minus sine squared and then we can let sine be our u. So derivative here is going to be cosine x dx. So that's where I get this portion right here. So I'm going to say 1 minus u squared. And then cosine x dx is going to be du. And then we can integrate that. So this would become x, not x, u minus 1/3 u cubed plus c. So sine x minus 1/3 sine cubed x plus c. So that one a little bit more challenging. Got to remember trig identities and kind of puzzle it a little bit, but I trust that you can do it.